Continuing with this series of videos attempting to perhaps better describe some of the physical effects that are described in physics lectures, the causes more than the effects emphasis and such. So hopefully this will play correctly. So we're on electric circuits, which might end up being a bit tedious, mathematics, blah blah blah, not too interesting, so we'll try to do the best we can with it and such.
When positive charges move in this direction, then per definition we say the current goes in this direction. When negative charges go in this direction, we also say the current goes in that direction. That's just our convention. If I apply a potential...
Okay, it's just their convention, he says. But it's sort of important well, first off, okay, we have these horrible sign assignments, basically backwards. You know, where the excess of electrons has a minus sign and the absence of electrons has a plus sign. So the low pressure is plus and the high pressure is minus. Just really bad. And then we're talking as if there's a voltage difference this way, high to low, and the voltage goes from high to low, but somehow the current, or the substance of the stuff, goes from low to high. And I think that's just creates a mess. Part of the way I would get around it is to point out that the voltage difference, once you're allowing the voltage to move, the high voltage moves, the voltage moves all the way to the other end. And so the current and the voltage are moving in the same direction, in the sense that the voltage difference is felt at the other end and ends up going from that high to the low. The same direction as the current.
Difference over a conductor, then I'm going to create an electric field in that conductor.
Alright, so again we're back to this argument that they're going to describe everything based on what this field effect is, rather than describing it based on the cause of the field effect. That is, what difference in the system is creating the field effect. So I would just argue that it would be more fundamental to go to the cause of the effect, which is the imbalance in the pressure, the difference between electron heavy atoms and electron light atoms that are actually creating the change in the field, in the energy that's moving away from those atoms. So the atoms are reflecting or transmitting a change in the energy profile they're getting exposed to. They're filtering the energy, producing a change, and that change is what's going to move down the wire. There's no field moving down the wire, technically.
And the electrons, there are free electrons in the conductor. They can move, but the
Okay, let's understand. The word free is kind of a dirty word here, because I could just have two ions attached to each other, an atom that's short an electron, an atom that's got too many, and they could be next to each other, tied to each other, and you wouldn't know which one is which until they break apart. You know, this one can go 3 and this one can go 5, or vice versa. So that's sort of this flow of electricity. It just depends on which atoms, the right ones or the left ones, are the ones that are going to 3 versus the ones that go to 5. So you know, and the idea is that there's electrons that are in metals, and you can kind of see metals are not, you know, they're not something you just blow on it and blow a bunch of these free electrons out of it like they're just free. They're really not free. They're stuck and they transmit. So you have one that has 6 electrons and this one has 4 electrons, and the electron can, it's free enough to move between the two and turn this into a 5 and turn this into a 4, you know, that kind of thing. So it's free is a deceptive word, I think, in this context. I don't think electrons are ever free. There's always a difference in the field around them that they can detect, and they'll be obligated to move in that direction.
Cannot move because they are frozen into the solid, into the crystal. And so when a current flows in a conductor, there's always the electrons that are responsible for the current.
So again, I think it's very deceptive. The electrons are frozen in positions, and all that's really happening is red hits brown, brown turns red, red hits brown, brown turns red, red hits brown, brown turns red. They're not really going anywhere. They're just transmitting a state. So the state of this atom is being transmitted to this atom, it's being transmitted to this atom, it's being transmitted to this atom.
Electrons feel the electric field, and then the electrons try to make the electric field zero, but they can't succeed because we keep the potential difference.
So they're not trying to do anything, they're just doing the natural thing, which is any disruption, like dropping water droplets into the water. The water's not trying to be neutral. It just will become neutral as all the little bits hit each other, and so much, we can see it kind of happen with water. What's happening with electricity is happening much quicker, but it's the same. It's just being neutralized by the fact that the system has it will go to balance. It can't be unbalanced. It's like you can't drop food coloring into the water without it changing the color of the water, or however you want to look at it. If it's the same temperature and has the same molecular structure, just a different color, it's just going to end up mixing with the other atoms just through this vibrating. Vibrating is probably a good way to describe it. I mean, the system's vibrating, and it's like a box of sand or something. It'll just always keep going flat. You can poke holes in it, and it'll just keep going flat. It's not trying to make it flat. It's just the physics.
But the conductor. Often there is a linear relationship between current and the potential, in which case we talk about.
So he's just saying there's a proportional relationship between voltage and current. So the higher the pressure, the more likely you are to have current. You could say, the higher the pressure of the water hose, the more likely a lot of water will come out if you open it.
About Ohm's law. Now I will try to derive Ohm's law in a very crude way, poor man's version, and not really 100% kosher.
So by derive, I guess he sort of means I want to try to find that it has roots in these basic functions, and he's just going to be selective about what functions. So in a sense, you could derive it by coming up with all kinds of ideas about electrons moving certain distances in a certain amount of time, blah blah blah. And the reality is those relationships could just have to do with how often atoms bang into each other rather than how often electrons do. You could use any kind of relationships to derive the product, because we know the product's generally correct because the product is observed. So he's just kind of, he's like all these things, like he just pointed out, there's a relationship between current and voltage. All these things are related, and so you can choose any one of the variables to put into an equation to decide this is what the cause is. But the cause isn't that select bunch of variables. The cause is that these variables are related. They're paired to other variables. So it isn't, it's not kosher to think that these derivatives have any true relationship to the actual variables that are causing the effect.
Requires quantum mechanics, which is beyond the course, becomes this course, but I will do a job that still gives us some interesting insight into Ohm's law.
Yes, it doesn't require quantum mechanics. It wouldn't improve much any of the equations, and to add this random nonsense, because most of the random nonsense just has to do with getting rid of everything on the left and right side anyway. For every effect that goes right, there's an effect that goes left. You just annihilate those and you end up with a straight line anyway.
If I start off with a conductor, for instance copper, at room temperature, 300 degrees Kelvin, the free electrons in copper have a speed, an average speed of about 1,000,000 meters per second.
Alright, so these are just pulled out of their sort of any place. numbers, they don't measure the speed of electrons.
So this is the average speed of those free electrons, about 1 million meters per second. It is in all directions. It's a chaotic motion.
It's a pressure that isn't in a direction, and for voltage to be realized, the pressure really does have to be in a direction, from high to low or something. So you could argue it's a kind of pressure, a kind of voltage, a kind of activity, but it isn't coherent, so it doesn't have any meaning. Because it undoes everything it does this way, it does something that way. Everything this way, it does something that way. So it's all undone as an effect, where voltage is a direction. There's more this way than there is that way. There's more this way than there is that way.
The thermal motion is due to the temperature. The time between collisions, between the collisions, this is the collision of the free electron with the atoms.
So, these are their premises, and we never get details on how any of these experiments were done to detect any of these numbers, besides doing experiments based on the effect and some other set of assumptions that dictate, well, if the electricity gets from point A to point B at a certain speed, I have to account for how it did that, and if I know the atoms can only go this fast, then I have to assume the electrons are making up the difference. So if their theory of how the electricity is moving is wrong, then these numbers are nothing. So you can't take them too seriously.
It is approximately, I call it tau, is about 3 times 10 to the minus 14 seconds. No surprise, because the speed is enormously high. And the number...
So again, all of this is just an assumption based on their previous assumed model. So if you assume electrons orbit around protons and that the orbit is somehow controlled by some force like gravity or bent space or whatever you have to come up with, then you have to have a certain speed of the electron for it to stay in the orbit of the proton, and you have to come up with a whole theory. But that's just theory. Those aren't facts.
Free electrons in copper per cubic meter, I call that number n, is about 10 to the 29. There's about 1 free electron for every atom. So you get 20.
Yeah, so you're almost talking like, yes, every atom is potentially an ion, because there's an ambiguity to their state. They're neither male or female until you start breaking them apart and doing certain things. Then you can figure that out, and then they start to polarize. All the women go one way and all the men go the other way, or something like that. But it's just sort of an indication that these aren't really free electrons. These are identity electrons. These will dictate the identity of a particular atom, but they'll be able to transmit force between atoms by, if it leaves a high pressure atom and hits a low pressure atom, the electron will obviously impose pressure on the lower pressure atom. So they can be used, but it's not much different than, as I stated before, two atoms being loosely associated, a 3 and a 5, loosely associated by an electron that can go either way. So, same difference.
To the 29 free electrons per cubic meter. So now imagine that I apply a potential difference, piece of copper, any conductor for that matter, then the electrons will experience a force, which is the charge of the electron. That's my little electric field that I'm creating. I apply a potential difference. I realize that the force and the electric field are in opposite directions for electrons, but that's a detail. I'm interested in the magnitudes only.
Yes, well...
And so now these electrons will experience an acceleration, which is the force divided by the mass of the electron. And so
why this keyboard thing just doesn't work.
We'll pick up
There we go. Kind of lost the point that I was... it's current and voltage again. So again, he's saying how, well, we have the convention of them going the opposite ways, and I'll just ignore that for now. It's just unfortunate that it has to be ignored, because it just creates nothing but confusion.
Speed between these collisions, which we call the drift velocity, which is 8 times tau, which is 801.
So this drift of velocity just has to do with what their estimate is of, how much progress electrons make going through the conductor. and the drift velocity ends up being preposterously slow, and the whole thing doesn't make much sense. And so, I don't know, like I said, I don't know how useful this mathematics is when it has in it an obvious defect, essentially, where you can just say, well, the electrons can't possibly be migrating that slowly, and you transmit enough force to, run a big motor or something. And you're obviously running it at almost this, when you hit the switch, it didn't take 6 hours for the motor to start running.
And so A equals F divided by ME, F is in A, so we get E times E divided by the mass of the electrons times tau. And that is the drift velocity. When the electric field goes up, the drift velocity goes up, so the electrons move faster in the direction opposite to the current. If the time between collisions gets larger, the acceleration lasts longer, so also they pick up a larger speed, so that's intuitively pleasing.
Yeah, I'm sorry, it's really not, to me, anything to talk about going against the current. The electrons are moving this way, the current's moving this way. You're already dead in the waters, so to speak.
If we take a specific case, and I take, for instance, copper, and I apply over the wire, let's say the wire has a length of 10 meters, I apply a potential difference I call delta V, but I could have said just V. I apply there a potential difference of 10 volts, then the electric field inside the conductor now is about 1 volt per meter. And so I can calculate now for that specific case, I can calculate what the drift velocity would be. So the drift velocity of those free electrons would be the charge of the electron, which is 1.6 times 10 to the minus 19 Coulomb. The E field is 1, so I can forget about that. Tau is 3 times 10 to the minus 14 as long as I'm room temperature. And the mass of the electron is about 10 to the minus 30 kilograms. And so if I didn't slip up.
So, I mean, these are just, obviously a constant and essentially a constant, and the weight of the electron, which is another constant. So, I don't know. There's an equation made out of constants. Just not surprised as an answer, but it's 3 constants.
I found that this is 5 times 10 to the minus 3 meters per second. It is half a centimeter per second. So imagine, due to the thermal motion, these free electrons move with 1,000,000 meters per second. But due to this electric field, they only advance along the wire slowly, like a snail, with a speed, an average of half a centimeter per second.
So again, this is all based on their assumption that the energy is the electron, because they don't understand that the electrons are just being pushed by a force. So the force is what's really moving. The electrons are just conduits to, they're little bits of vibration. They vibrate quicker this way and slower this way. They're just being conduits to the transmission of the force from one end to the other end. They're not the force. The force is moving the electrons and not moving them. Like I said, the electrons don't need to go anywhere. They just need to convey pressure information from one atom to another atom, and just say high pressure atom, pressurized low pressure atom. And then this becomes a high pressure atom, and it's next to a low pressure atom. It says, pressurized low pressure atom. It's just, it ends up just being a stick being poked, and the drift velocity is quite irrelevant.
And this goes very much against you and my own intuition. This is the way it is. I mean, a turtle would go faster than these electrons.
So he just says it's the way it is. It doesn't sound quite right. It's a little bleh. And it's based on a bunch of huge number of assumptions, you could say. It's pretty weakly evidenced, but it's the way it is. No, we could just assume that maybe this line of thinking is incomplete. It needs some more work.
To go along a 10-meter wire would take half hour. Something that you never thought of. That it would take half hour for these electrons to go along the wire if you apply potential difference of 10 volts, copper 10 meters long.
Yes, I wouldn't have thought of it, and I would say if you're going to tell me, just like I wouldn't think there would be, whatever, 400-foot tall aliens invading Earth. I wouldn't think of that either necessarily as a truth, unless somebody showed me some really good evidence. And we're not shown any of that good evidence stuff.
Now I want to massage this further and see whether we can somehow squeeze out Ohm's law, which is the linear relation between the potential and the current. So let me start off with a...
Okay, so it's basically just an argument about resistance in the end. That's what Ohm's law is. So when he says the relationship between the voltage and the current, he's just sort of making the argument that you'll see more of the imperfections. Like I'll use the stream analogy. If water's flowing through a stream and there's some rocks in it, the rocks are going to be the water's going really weak volume. The rocks aren't too big a deal because the water can just meander through and it's not a big deal. But if you got a high pressure, a lot of water going down a steep hill, the rocks become a real problem because there's a lot of scatter, a lot of energy going in the wrong direction. They create a real obstruction. So when water is meandering, not too big a deal, but when the higher the pressure gets, the more the obstructions become a huge problem. And that's resistance.
Wire, which has a cross-section A, and it has a length L. And I put a potential difference over the wire, plus here and minus there, potential V. So I would get a current in this direction. That's our definition of current. Going from plus to minus. The electrons, of course, are moving in this direction with the drift velocity. And so the electric field in here, which is in this direction, that electric field is approximately V divided by L. Potential difference divided by distance.
Yeah, he's just to say pressure difference. No, just forget about the field. The field isn't doing anything. The field is a byproduct of the pressure difference. The pressure difference is going to be the field. As the pressure moves, that's the field. The field is made of the force. The force is the pressure. The force is going to move. The force doesn't make the force. The force is the force. The pressure is the force.
In one second, these free electrons will move from left to right over a distance VD meters. So if I make any cross-section through this wire, anywhere, I can calculate how many electrons pass through that cross-section in 1 second. In 1 second, the volume that passes through here, the volume is VD times A.
So again, these are just subtle proportional relationships. You can sort of understand that the more current you're moving, that is, the more pressure you're moving, the more action that's going to be required to move pressure, and they're just associating action with electrons moving, and the action is really just the force moving.
But the number of free electrons per cubic meter is called N. So this is now the number of free electrons that passes per second through any cross-section. And each electron has a charge E, and so this is the current that will flow. The current, of course, is in this direction, but that's a detail. If I now substitute the drift velocity, which we have here, I substitute that in there, so then I find that the current, I get a E squared, a charge squared, I get N, I get tau, I get downstairs the mass of the electron, and then I get A times the electric field E. Because I have here this electric field E.
So he's just saying that there's an amount of conductor A, there's a known amount of tau or impediment, and the other things are all constants. Dependent are constants dependent on voltage. So the higher the voltage, the constants change. But that's it. So the higher the voltage, the more the impediments become relevant dependent on the area. So if you have 10 rocks and you have a gigantic area, you're okay. But if you have 10 rocks and you only have a small area, you're not going to be okay.
When you look at this here, that really depends only on the properties of my substance for a given temperature.
As I just pointed out, it's all constants. It's just really based on a K factor of something. Yeah.
And we give that a name. We call this sigma, which is called conductivity.
Or resistance. Lack of conductivity. It's called either one.
Conductivity. If I calculate for copper the conductivity at room temperature, that's very easy, because I've given you what N is. On the backboard here, 10 to the 29. You know what tau is at room temperature, 3 times 10 to the minus 14. So for copper, at room temperature, you'll find about 10 to the 8th.
So these numbers really don't have anything to do with all that other crap. You could derive the relative difference between the different conductors through any mechanism. You know, experiment, just demonstrate how one is more efficient, gets less hot than the other, and demonstrate their relative difference, and then just apply a 10 to the 8th for copper, and 10 to the 9th for this, and 10 to the 10th for that, and, you know, so this is really quite arbitrary.
We'll see more values for sigma later on during this course. This is in SI units. I can massage this a little further because E is V divided by L, and so I can write now.
It is all just manipulations, you know, that don't necessarily have any direct correlation to what's actually causing the effect.
That the current is that sigma times A times V divided by L.
So length, area, so obviously that's your total amount of substance, essentially. And the rest of it's just a constant. The voltage isn't a constant, but it's, you know, a known variable kind of thing when you're trying to do current.
I can write it down a little bit differently. I can say V therefore equals L divided by sigma A times I. And now you're staring at Ohm's law, whether you like it or not. Because this is what we call the resistance, capital R. We often write down rho for 1 over sigma, and rho is called the resistivity. So either one will do.
So you just use the inverse of the number and call it rho. Yeah, okay, fine.
So you can also write down V equals IR, and this R then is either L divided by sigma A or L times rho. Let me make it a nicer rho divided by A. That's the same thing.
Right. So Ohm's law is the V equals IR, and you convert the R into the factors that make the R, which are the area, the volume of the conductor, and the standard of impediment. How much natural impediment does that substance have? So it's basically a constant.
The unit for resistance R is volts per ampere, but we call that ohm. And so the unit for R is ohm. And so you want to know what the unit for rho and sigma is, it follows immediately from the equations. The unit for rho is then ohm meters. So we have derived the resistance here in terms of the dimensions, namely the length and the cross-section, but also in terms of the physics on an atomic scale, which all by itself is interesting.
So again, he says he's paying attention to the physics, but it's not the real physics, because you can have any diagram fit the simplicity of the facts, which is a certain amount of pressure is going to end up from one point to another, and I can come up with all kinds of analogies for how that pressure goes from one place to another. I can use a stream analogy, an impediment analogy. I could use some sort of relativity argument that the amount of the area of the wire gets smaller as you put more current through it. I can come up with lots of scenarios that explain the effect, but doesn't mean they're right.
If you look at the resistance, you see it is proportional with the length of your wire through which you drive the current. Think of this as water trying to go through a pipe. If you make the pipe longer, the resistance goes up, so that's very intuitively pleasing.
Right, but a pipe's resistance is basically in the surface tension with the pipe, and in this case, but say that's another analogy. I think the impediment thing is more closer to the truth, that the substance you're putting it through isn't pure enough, just the way it is. It's got impediments in it. It's got parts in it where the atoms, it's got little bits of an insulator in it. And the little bits of insulator mean that the pressure isn't transmitted from one atom to the other atom. So the pressure goes in and it reflects back the wrong way, essentially. And that is just absorbing some of your capacity to get the total energy through the medium. So if you have little bits going the wrong way, here and there, that's just subtracting from how much you're going to get at the end. And it's also creating, negative. it's creating a negative effect in the sense that it's creating motion in the wrong direction, and might, in a sense, it's a good analogy. It's enlarging the impediments. So when it goes the wrong way, it hits another impediment, makes it a little bigger. So it's even more of an obstacle for the next thing to hit. And so every time it gets hit, the impediment gets a little bigger. And so as you hit more impediments, you make the thing more resistive. And that's how resistors work, essentially, is the more you try to force stuff through the medium, and it's going fast enough to hit those rocks, without meandering around them, you get more splashes, more reflections, more water going off the shore, and essentially you're creating heat, but the amount of losses are increased. And so that's what resistors do. As they get hotter, as you try to force more pressure through them, the resistance goes up.
That you have A downstairs. That means if the pipe is wider, larger cross-section, it's also easier for the current to flow, easier for the water to flow. So that's also quite pleasing. Ohm's law also often holds for insulators and not conductors, even though I have derived it here for conductors, which have these three electrons.
So it is a subtle effect that I think needs to be emphasized, that the curve is kind of not straight, linear, in the sense that at low pressure, resistance is very irrelevant almost. It doesn't have much of an effect. And at high pressure, it has a lot of effect. But it does it on some kind of strange line. So the fact is that for... I said that the wrong way. The current is going to matter. So you could have high pressure, but the high pressure dissipates into a small stream. So it's like putting a garden hose to make a stream 4 feet wide. The water will meander instead of banging into the rocks. So you can still have you can maintain your pressure through the resistor if you're not shoving too much fluid through it. So if the current is low enough, the resistor is less resistive in a sense. It's something along those lines. It has to be. Voltage doesn't drop if current is low.
And so now I want to make a comparison between very good conductors and very good insulators. So I'll start off with a chunk of material. Cross-sectional area A. Let's take it 1 millimeter by 1 millimeter. So A is 10 to the minus 6 square meters. So here I have a chunk of material, and the length of that material L is 1 meter. Put a potential difference over there, plus here, and minus here. Current will start to flow.
You know, it simplifies things to use a square conductor, I guess, because then you don't have to do the, you know, conversion to, you don't have to use pi to get to your area. You can just do a simple area calculation. So I suppose that's why I used a rectangle.
In this direction, electrons will flow in this direction. The question now is, what is the resistance of this chunk of material? Well, very easy. Take these equations, you know, L and A. If I tell you what sigma is, then you can immediately calculate what the resistance is. So let's take first a good conductor. Silver and gold and copper are very good conductors. They would have values for sigma 10 to the 8. You just calculate it. You've seen it in front of your own eyes. So that means rho would be 10 to the minus 8. It's 1 over sigma.
Well, we didn't see anything, but you tell us what the number was, so you didn't see it with my own eyes. But anyway, close enough.
And so in this particular case, since A is 10 to the minus 6, the resistance R is simply 10 to the 6 times rho. Because L is 1 meter. So it's very easy. The resistance here, R, is 10 to the minus 2 ohms. 1/100 of an ohm. For this material, if it were copper. Let's now take a very good insulator.
So
Glass is an example. Quartz.
The point is as you increase the length of any of this stuff, you're going to increase the number of rocks, and that's just a fact. So the longer the wire is, the more rocks in the stream, the slower the end result's going to be. The more losses there's going to be. So the more drop in your pressure.
Porcelain. Very good insulators. Now sigma, the conductivity is extremely low. They vary somewhere from 10 to the minus 12 to 10 to the minus 16. So rho now, the resistivity, something like 10 to the 12 to 10 to the plus 16. And if I take 10 to the 14, just like I have to grab a number, then you'll find that R now is 10 to the 20 ohms. A 1 with 20 zeros. That's an enormous resistance. So you see the difference, 22 orders of magnitude difference between a good conductor and a good insulator. And if I make this potential difference over the wire, if I make that 1 volt, and if I apply Ohm's law, V equals IR, then I can also calculate the current that is going to flow. If IR is 1, then the current here is 100 amperes, and the current here is 10 to the minus 20 amperes. Insignificant current, 10 to the minus 20 amperes. I first want to demonstrate to you that Ohm's law sometimes holds. And I do a demonstration whereby I have a voltage supply, put a V in here, and we change the voltage in a matter of a few seconds from 0 to 4 volts. This is the plus side. This is the minus side. I have connected it here to a resistor, which is 50 ohms. We use this symbol for a resistor. And here is a current meter. And the current meter has negative resistance, so you can ignore that. And I'm going to show you on an oscilloscope. We've never discussed an oscilloscope, maybe we will in the future. I'm going to show you there projected the voltage, which goes from 0 to 4, versus the current. And so it will start here, and by the time we reach 4 volts, then we would have reached a current of 4 divided by 50, according to Ohm's law.
So that's basically just saying, as I pointed out, the pressure has to move, and the current, they're saying, is going in the opposite direction. Well, realistically, what's going to happen is the pressure is going to be realized at the other end, and that's when you can move the full volume of whatever you have. So until the pressure is felt through the whole stream, there isn't a whole stream yet. It takes the water a little bit of time to get to its full volume, and that can be measured as voltage in the sense that when the water, like if there's a stream 100 feet away and somebody just puts water in there, the first bits of water will be trickles, and then it will build up and build up. And so that's what this line represents, is that there's a little bit of a time lag between when you start your pressure migration and you're up to the full stream. I think that's a good enough way to say it.
I will write down this 4 divided by 50 amperes, which is 0.08 amperes. And if Ohm's law holds, then you would find straight line. That's the whole idea about Ohm's law. That the potential difference linearly proportional to the current. You double the potential difference, your current doubles. So let's do that. Let's take a look at that. You're going to see that there. And I have to change my lights so that you get a good shot at it. Oh, it's already going. So you see, horizontally, we have the current, and vertically, we have the voltage. And so it takes about a second to go from 0 to 4. So this goes from 0 to 4 volts, and you see that the current is beautifully linear. Yeah, I'm blocking it. Oh no, no reflection. That's interesting. Ohm's law.
So what would have been kind of interesting is to take a very long wire, sprawled all out, and do a short wire, then do the very long wire, and see if you can lengthen that line.
It doesn't allow for that. So you see how beautifully linear it is. So now you may have great confidence in Ohm's law. Don't have any confidence in Ohm's law.
That's kind of an annoying statement. It's not a law. It's just the idea that it's a regular. It's a regular property. It's a regular. It's a routine. It's a tendency, a very strong tendency. These relationships, but you can do things to screw it up. You can squish the hose. You can you can throw more rocks into the stream. You can do things to mess up the relationship, but you have to, essentially something has to happen, and there's causes for those effects. So the exceptions are exceptions for a reason.
The conductivity, sigma, is a strong function of the temperature. If you increase the temperature, then the time tau between collisions goes down because the speed of these free electrons goes up. It's a very strong function of temperature. And so if tau...
All right, a way to analogize temperature might be to say there's a bunch of sand on the bottom, and as stuff happens, interactions, the sand gets stirred up, and then those particles end up being another impediment to flow because little bits hit the sand, and the sand doesn't move very fast, and blah, 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 blah. So it's another lagger, would be the fact that as you start agitating, you move this other crap into you create heat, and the heat is another form of impediment.
Goes down, then clearly what will happen is that the conductivity will go down. And that means rho will go up. And so you get more resistance. And so when you heat up the substance, the resistance goes up. Higher temperature, higher resistance. So the moment that the resistance R becomes a...
So I just point out, my own experience with this is that I did do some work in electronics, and resistors comes in all kinds of standards. So you can precision. You have a thing called a precision resistor, which would be like a NASA would use the precision resistors, and they're made to be have less sand, less capacity to be disturbed by heat. So you can have cheaper resistors that they're really heat flexible. So a little bit of heat and they start changing their resistance. And you can have other resistors that are just made better, and so they will be less affected by changes in heat and less capable of producing heat.
Function of the temperature, I call it a total breakdown of V equals IR, total breakdown of Ohm's law. If you look in your book, they say, oh, no, that's not a breakdown. You just have to adjust the resistance for a different temperature. Well, yeah, that's an incredible poor man's way of saving a law. It's a very bad law.
No, I'm just saying it's not a law in the first place, and clearly that can be understood that heat generated from the external world or from the process of trying to shove way too much crap through too small a stream bed, right? The stream bed's this big, you try to push more water in and you start ripping mud off the banks and all that kind of stuff. So yeah, it's vulnerable. The not function. The jeez, I just hate this words that disappear thing. The idea that you made a formula, you formalized this general effect of water going through streams. And yes, there's circumstances that you can understand where, you have a flood zone or some of the, things, circumstances that change, and then once that change takes place, yes, not all bets are off, but you have to understand the effect on the formula. The formula has to change as you change the conditions.
The temperature.
I mean, you could argue it's an incomplete formula without obliging you to have some sort of temperature coefficient in the formula. So you could say, okay, let's improve Ohm's law by saying temperature coefficient, divided by, well, multiplied by in this case.
Itself is a function of current. The higher the current, the higher the temperature. And so now you get a ratio V divided by I, which is no longer constant. It becomes a function of the current. That's the end of Ohm's law. And so I want to show you that if I do the same experiment that I did here, but if I replace this by a light bulb of 50 ohms, it's a very small light bulb. Resistance when it is hot is 50 ohms. When it is cold, it is 7 ohms. So our code of the light bulb.
So obviously light bulbs are deliberately made to have a lot of impurities in them. So the impurities create heat and then light. They're deliberately made to get hot. It's a deliberate breaking of the resistor, the function of a resistor, the common function of a resistor, which is to do a stable amount of impeding. That's not what a light bulb filament is intended to do. It's intended to make light. It's intended to be unstable.
It's roughly 7 ohms, I believe. But I know that when it is hot, it's very close to 50 ohms. I think it's a little lower. What do you expect now? Well, you expect now that when the resistance is low in the beginning, you get this. And then when the resistance goes up, you're going to get this. I may end up a little higher current because I think the resistance is a little lower than 50 ohms. And if you see a curve like this, that's not linear anymore. So that's the end of Ohm's law. And that's what I want to show you now. So all I do is here I have this little light bulb. Those of you who sit close, they can actually see that light bulb start glowing, but that's not important. I really want you to see that V versus I is no longer linear. There you go. And every time you see this light bulb go on, it heats up, and during the heating up, the resistance increases. And it's the end of Ohm's law for this light bulb at least. It was fine for the other resistor, but it was not fine for this light bulb. There's another way that I can show you that Ohm's law is not always doing so well. I have a 125 volt power supply. So V is 125 volts. This is the potential difference. And I have a light bulb. You see it here. That's the light bulb. The resistance of the light bulb, cold, I believe is 25 ohms. And hot is about 250 ohms. A huge difference. So if the resistance, if I take the cold resistance, I would get 5 amperes, but by the time that the bulb is hot, I would only get half an ampere. It's a huge difference. And what I want to show you, again with the oscilloscope, is the current as a function of time. When you switch on a light bulb, you would expect, if Ohm's law holds, that when you switch on the voltage, that you see this. This is then your 5 amperes. And that it would stay there. That's the whole idea. Namely, that the voltage divided by the current remains a constant. However, what you're going to see is like this. The resistance goes up, and then therefore the current will go down, and will level off at a level which is substantially below this. So you're looking there, you're staring at the breakdown of Ohm's law.
Yeah, well, the point being that I guess that's what we commonly see is when you first turn on the light, there's this surge, and then it goes down to a steady voltage based on the fact that the resistance of the bulb goes up. So the initial resistance is really low, so a whole bunch of stuff goes through. It starts agitating the bottom of the stream. It starts, creating more of this bulk. There's more bulk to move. So bulk has been added to the pressure, and now the pressure has to push the bulk. And so the volume starts to decrease from that initial push because now it's got to push this sludge with it.
So that's what I want to show you now. So here we need 125 volts. And there's the light bulb. And when I throw this switch, you will see the pattern of the current versus time. You only see it once, and then we freeze it with the oscilloscope.
The line also represents the voltage drop. So as that line goes down and steadies out, it means the voltage drop is not as big. So it's big voltage drop in the beginning, and then it levels off at a less voltage drop. I think I said that the right way.
Turn this off. So look closely now. There it is. Forget this little ripple that you see on it. It has to do with the way that we produce the 125 volts. And so you see here horizontal the time between two adjacent vertical lines is 20 milliseconds. And so indeed, very early on, the current surged to a very high value, and then the filament heats up, and so the resistance goes up, the light bulb, and the current just goes back again. From the far left to the far right on the screen is about 200 milliseconds. That's about 2 tenths of a second. And here you get a current level, which is way lower than what you get there.
Right, so you always have to be kind of aware of that. Like everything has this surge. It's a common word in electronics. And yeah, the surge is a substantial, 3 times higher amount of current. And so you have to make things that are capable of tolerating this, forcing more pressure through the small hole kind of thing for a short amount of time.
It's a breakdown of Ohm's law. It is actually very nice that resistances go up with light bulbs when the temperature goes up. Because suppose it were the other way around. Suppose you turn on a light bulb and the resistance would go down. Light bulb gets hot. Resistance goes down. That means the current goes up. Instead of down, the current goes up. That means it gets hotter. That means the resistance goes even further down. That means the current goes even further up. And so what it would mean is that every time you turn on a light bulb, it would right in front of your eyes destruct itself.
Right, so there's lots of electric circuits that can have that runaway effect, and you just create another circuit that basically measures the temperature and then creates another change in the system to absorb that problem. So you can make knee jerks that take care of the problem, reflexive circuits that react to the tendency to get out of control.
That's not happening. It's the other way around. So in a way, it's fortunate that the resistance goes up when the light bulbs get hot. All right. Let's now be a little bit more quantitative on some networks of resistors, and we'll have you do a few problems.
All right, so I guess we're at a good point to say that's enough for this episode. Might get worse, might get better. We'll see. It's not bad. It wasn't as bad as I thought it would be. Just remembering circuits. You don't just start doing all this circuit stuff and all this math, and it's just kind of routine kind of stuff. I'm not saying it's worth knowing how to do all that stuff. I'm just, especially if you're in the business, but I'm just saying it is kind of, it's not terribly interesting as raw physics. It doesn't have much to do with mechanics. It's just formalizations. Okay, so that's enough of that, and I have to go somewhere to complete the video. Okay, So till the next time and such.